I don't think, do I need this microphone? I don't think I do. Nothing is not allowed now. But I do want to thank the organizers of the conference for allowing me to talk on isolation and information flow in quantum systems. As Howard said, this is joint work with Benjamin Schumacher. And the title basically gives the structure of the talk. I will say a bit about something called the isolation theorem, and then pass on to talk about more general information flow in quantum systems. And time permitting, say a few words about a specific quantum channel in view of these results. And secure this and try to go on. Okay. So. As I say, we will try to go on. There we go. Okay. Usually, when I think about giving a talk of this length, 30 minutes, 15 minutes, even an hour, I think at best what I should aim for is a sales talk. And usually the sales talk is to get you to invest some of your time, usually to read a paper. In this case, I'm going to do something more explicit. I'm going to do a sales talk about this book. It's Quantum Processes, Systems, and Information, written by a marvelous fellow named Benjamin Schumacher and some guy named Westmoreland. And the reason I bring the book up is that the motivation behind the isolation theorem comes from a discussion that we begin the book with. At the end of chapter 1, we talk about the double slit experiment and suggest the t-shirt slogan that quantum mechanics is what happens when no one is looking. And the double slit experiment, which we all know and love, is a prime example of that. You remember the results that the, whoops. Well, it's not going to allow me to do that. It's not allowing the animation effects. Maybe questioning tool around this computer, and I've lost my cursor. And
It's on the other side.
there we go. All right, so you remember the results. If only the left slit is open, we get a pattern of light on the screen. Only the right slit is open, we get a shifted pattern. But if both slits are open, we get the famous interference effect. And we only get that if we don't know which slit the electrons or photons or whatever the system is that's passing through our screen. Only if we don't know which slit those particles transfer, actually information isolation. When are we in a situation where we get interference effects, where the superpositions in some sense matter in a physical way? And the first pass at this is to try to pin down what is meant by information transfer. If the state of E depends on the input state of Q, then heuristically we say that Q is not informationally isolated from E. And as is often the case in mathematics, it's actually easier to pin down when something doesn't happen. So that's the reason why we have the isolation theorem. And of course, in this case, or in the case that motivated this idea, things like the double slit experiment, interference effects, entanglement effects, it's really the informational isolation that we're interested in, and it's what we're hoping for was some mathematical characterization of information isolation. And so this setup is specifically to address this notion that of which the double slit experiment is a prime example. That if we have a system of interest and an environment, say an observer, if the observer doesn't obtain any information about Q, then we say Q is informationally isolated from E, from the environment. And so if the output of E here after the action of Q is independent of the input state of Q, then we say that Q is informationally isolated from the environment. So this leads to this theorem that if we characterize information isolation in that way, then Q is informationally isolated from E if and only if the evolution of the composite system is in fact unitary on Q. And I agree with Professor Baez that you don't want to give a proof in the middle of a particularly short talk. I do want to indicate the elements of the proof very quickly. The if direction, that if the evolution on Q is itself unitary, then the derivation is mostly straightforward. That the only complication being that in the body of the proof, you pick two arbitrary input states for Q and show that the output at the far end of E is the same in each case. If you're unlucky and you pick what the states in the beginning states of Q to be orthogonal, the general argument doesn't quite go through, but then you just pick some state that is not orthogonal to those two states, say the superposition of both of those, and then the argument is in fact quite straightforward in that direction, that if the evolution of Q is itself unitary, then we have information isolation. The harder direction is to start out assuming that you have information isolation, and the elements of the proof involve the Schmidt decomposition on this overall unitary of the input with the initial state of E being in this fixed input state. And then we take that Schmidt decomposition and build these V sub k operators. And then the rest of the proof involves, and it's the tricky bit, showing that these operators satisfy these conditions. And if you look at those long enough, what you conclude is there's only one such V sub k operator that is in fact the unitary that's acting only on Q. So that's the situation where we're looking at a case like, as I said, the double slit experiment, where you have one system of interest there's the rest of the universe, but in between those two, there's a neighborhood of A that, if we just knew the beginning state of B, then we could determine the state of A after the action of some dynamics. And we don't, it would be a bad thing if we had to know the state of the rest of the universe in order to specify what happens to A. So this is the motivation for this bullseye picture. You don't want to have to know whether or not you're standing up or sitting down in the double slit experiment, along with the state of the electron source, say, in order to determine which slit the electron goes through. Usually, the state of the human observer isn't relevant, nor is the position of Saturn at that moment. So this is a reasonable way of looking at this, to be able to decompose things into system of interest, the part that affects the system of interest, and everything else that we can ignore. Causally, this is probably better looked at as a chain, that A depends directly on B, and there's no information transferred from C back to A. So, what can we say in this more general situation about information flow? Well, again, this is going to look very much like the previous discussion about an observer or just a simple environment and a system of interest. Information flows from C to A only if or doesn't flow, or it flows from C to A only if the final state of A depends on the initial state of C. And I should tell you that this discussion is not historical. In other words, the isolation theorem actually came, and I'm really not kidding about the book, it really came about when we were trying to pin down this notion of information isolation in a more simple way, so that the isolation theorem actually comes after these more general results that I'm about to explain. So, but it's no surprise that the same sort of ideas are at play here. And again, the negative image of this, that to say that information flows from C to A means that the final state of this depends on the initial state of that. If it doesn't flow, then it's the negation of that, which you can read. But there are quantum difficulties. Remember, in the isolation theorem, we took advantage of the fact that our environment started off in a fixed standard state. But in general, there may be quantum entanglement between A and C. So the more general discussion involving this three-part decomposition is going to have to be a little more delicate. And so we have to be able to account for that. But before I talk about information flow in terms of quantum systems, let's think about a classical example. That is the classical CNOT. I'm assuming that everybody knows the CNOT. That turns out not to be terribly readable, does it? If the control bit is the top bit, if it's set in 1, then the target bit passes through unchanged. If it's set at 0, the target bit passes through unchanged. If it's set at 1, then the target bit flips. And so in this case, it's easy to see. if you just read those things. It's easy to see that this is reversible. The map is 1 to 1. And the final state of T, the final state of C does not depend on T. There's no information flow from T to C in the classical case, but there certainly is from C to T. So we do have, in this classical case, one-way information flow. But in the quantum case, it's a little more delicate. In the standard basis, I'm sorry, I'm trying to understand this. The screen that I'm looking at, the background here is blue. Black on blue is a little easier to see than black on purple. So I'm not sure why that's happening. But in the standard computational basis, it acts just as in the classical case. In fact, if you like, the way the quantum CNOT is implemented is you take the classical bits and just treat those as your basis for your qubit, and then build your gate to say, well, it acts linearly based on this on these basis states. But so we get a unitary operation, but we don't have one-way information flow. And again, this notion of superposition in quantum systems, just as back in the double slit case, this existence of superpositions creates opportunities, but it also creates differences. Where in the classical case you didn't have one-way information, or you did have just one-way information flow from C to T, but not the other way. If we look at this in the conjugate basis, if you notice, lines 1 and 3 here look like lines 1 and 2 up here. In other words, the roles of control and target, the roles of control and target have flipped. Plus, the second system is now the control bit, and the first system is now the target bit. So in this case, we get information flow in the other direction. So this equality isn't meant literally to implement the CNOT. You have to specify a basis, but once you have the system set up, if I fed in to this channel this plus minus set of states, then the output would act like this CNOT gate, where the control and target roles have switched. And so there is no one-way information flow on for this quantum CNOT. And it's even stronger, or there is an even stronger result than that. It's not just the CNOT. No unitary interaction leads to one-way information flow between quantum systems. Okay? So the situation where you would like to have a system of interest and not have monitoring of that system to affect it, that can't be implemented with things that are simply unitary on the system of interest. And so we are required to look at something more general. So this leads to this general picture of quantum systems, quantum dynamics, where the action on a given quantum tensor product structure. If I think of my system of interest, which we're going to do so in a big way here as part of a larger system, subsystem of a larger system, you want any extension of the action on the system of interest to this larger system to also be positive. And there are maps that are positive but don't extend to positive maps on larger systems where the subsystems are considered as tensor factors, if you like, of that larger system. The partial transpose is an example of that type of map, something that's positive but not completely positive. So again, let's remind ourselves what the picture is. And again, locality, at least this is the name we're going to go by here, is the evolution on, overall evolution on ABC is captured by this completely positive map, and there's no information flow from C to A if the final state of A depends only on AB. Okay? So what that implies is that there's some completely positive map that only requires the specification of AB to tell us what the value of A is. If you like, we can think of our AB system as the input, the lower system is input, the upper system is the output system of interest. So to know the state of affairs for A after our dynamics, if it only requires AB, that's what we mean by locality. And when we first started thinking about this issue, about to get this process down, I'll have it figured out by the end of the talk. But anyway, we sat around trying to figure out, well, what are some heuristic pictures, other possible pictures of locality that we can think of? And we came up with three. Are there others? Perhaps. It turns out these are the ones that were sufficient in order to derive the decomposition theorems that we derive. And locality one is this initial notion that I discussed before. The heuristic idea behind this, if you like, is that ignorance of system C doesn't hurt. Locality two, right, that the final state doesn't depend on the input for system C in this explicit way. What this, a heuristic way of looking at this is that, well, knowledge of C doesn't help. And the third one, right, a more operational picture, if you like, the heuristic idea behind that is, well, nothing I can do to C will change that situation. And as I recall, the implications are straightforward. That 1 implies 2 and 3 implies 1. The tricky bit is showing that 2 implies 1. But these are all equivalent characterizations of locality. So, and as I say, could there be other characterizations of locality? We couldn't come up with any. But as I say, those are the ones that are sufficient for the derivation of the decomposition theorem. So, and information isolation theorem. Then the overall evolution of QE is unitary, and then we discard the environment at the end. So this is one of the parts of the church of the larger Hilbert space that even if you're talking about an open system, well, if you append enough, the non-unitary action on the system of interest is in fact just part of a larger, or part of a unitary evolution on a larger Hilbert space. So we get to take advantage of the existence of such a representation for any completely positive map. Okay, so here E is the dynamics that we're interested in, the completely positive map. Unfortunately, over here, there is a slight difference in the boldface, but that's the environment system. The idea is that we can characterize this guy by acting on this expanding system and throwing away the environment at the end. So, if we have global unitarity in this three-part characterization of the universe, the question is, can we have global unitary with no information transfer from C to A? Well, here's one case where trivially that's the case. They're just isolated subsystems. You could have that situation, or we'd have that situation. That C and A act on separate subsystems that compose the system B. That would also be a situation where there's no information transfer from C to A, but the overall evolution is unitary. So, more interesting example is the following. I can have interaction between all three parts, but the interaction between A and B happens after or before, strictly before time flow is left or right. The interaction between A and B is strictly before the interaction between B and C. And so I can have information transfer from A to C, but not the other way. Okay, so this does allow for the information to flow from A to C, but not in the other direction. Okay, so the remarkable thing is this is the only possibility for A to be informationally isolated, for there to be no information transferred from C to A, but to have overall unitarity. And the main result of this is this decomposition theorem. So that if I have no information flow from C to A, and this is my overall unitary operation, unitary evolution, then I can decompose U into a unitary evolution just on A and B that acts before the unitary evolution between B and C. And I will dispense with the analysis of the CNOT. Just quickly note that the CNOT involves information exchange both ways. The question is, could this be modeled by simple information exchange? And the answer is systems, the surprising result by Michael Nathanson, who's now at St. Mary's College in San Francisco, is that no unitary, no entangling unitary qubit gate can be modeled by local CP maps and simple information exchange. And so I'll end with, again, the sales pitch. These are a series of papers that set out these results in more detail. The main results that of the earlier work are in this last paper, locality and information transfer. The application of these ideas is in this marvelous paper by Schumacher and Werner. It's to be revised. I saw it being revised last night. So, a local pizza. So, with that, I will end.
This information isolation theorem, isn't that just an instance of the Milnor-Flamm theorem? So in the Milnor-Flamm theorem for error correction. So in the following form, I mean, if you have a general channel, you can build a complementary channel that sort of measures the information flow to the environment. And then there is a theorem that tells you that if this complementary channel is depolarizing, then you are able to decode ideally the original channel. So this is basically the Milnor-Flamm theorem.
The complementary.
Also the complementary. So if you look at this as coupling to an environment, as you did, then the channel that goes from the original input to the environment is a complementary channel.
Okay.
Direct one. And in fact, this is also a stable statement. That is, if you know that it's almost depolarizing, you can conclude that it can be almost ideally corrected. So there's a lot of stuff around this.
It certainly sounds related, but
yeah,
I guess I don't see offhand how I can show that every instance of that would lead to polarizing channel in the complementary system or in the complementary channel.
Yeah, but this is an if and only if, and in fact you have bounds on the proximity of the complementary channel to the depolarizing and the decodability of the direct channel. You only use your direct channel was between two systems of the same dimension. Right? So if you allow the dimension to change there, then the statement would simply be that you can ideally recover the input information. And in this form, it's known as the Milnor-Flamm theorem, I guess.
Perhaps that's something we're discussing more at lunch, and probably we should move on to the next talk.
I have just a few minutes to tell you about what I guess Rob Speckens calls a foil theory. This is a imaginary world, imaginary theory, which has some of the features of quantum theory, but not all of them, and is really useful for sorting out the logical structure of quantum theory in relation to other ideas. And we're going to call it modal quantum theory for reasons that I'll explain in a minute. First I want to distinguish between the notions of probability and just possibility. And in our theory we're going to be going with the weaker notion of possibility. A probability, of course, the naive sort of way of thinking about probability is you have a set of events, and there's a probability measure on these events. Each possible event has a probability assigned to it. They sum to 1, and events with bigger probabilities are more likely. The events sort of aren't necessarily all equally likely. But then let's throw out the notion of probability and go with a much weaker notion of simply possibility. That is to say, you have a set of events, but you identify a non-empty subset. R is the set of possible events. And if it is in R, it's possible. It's not in R, it's impossible. And there's no additional concept of likelihood So these ideas of possibility and necessity are the ideas that are sort of captured by the idea of modal logic, if you've heard of that. We're not going to really do any modal logic here. Modal logicians like to consider questions like, well, if something is necessary, is it necessary that it's necessary, and things like that. But we won't need to do that. We just need the idea that all we're going to do is we're going to identify possibilities and impossibilities, and that's our only notion of the. We don't have a further notion of probability. Okay, so we're going to talk about quantum states. Of course, in ordinary quantum mechanics, what we will call actual quantum mechanics, the pure states are represented by normalized vectors in a Hilbert space, defined over the scalar field of complex numbers. But in our theory, what we're going to do is we're going to replace the field of complex numbers with a finite field. And most of what I say today will be for any finite field, but sometimes we'll also talk about specific examples. Just some finite field, and we have a vector space over finite fields. And notice that in this case, we have no inner product, and we have no norm. And without a norm, there's no normalization requirement. So in fact, any non-zero vector is a perfectly good state vector in our new quantum theory, our modal quantum theory. Nevertheless, we can do a lot of the usual things that we do in actual quantum theory. We can have coherent time evolution represented by a linear operator. In order to make sure you don't evolve into the zero state, you make sure these linear operators are invertible. The operators only act in discrete time. There's no continuous time evolution because this vector space is a finite object. It's a completely discrete object. So there's no continuous time evolution. And we can have a tensor product rule. Pure states of composite systems are just vectors in the tensor product vector space. Now, so let's talk about how we interpret this theory. A measurement corresponds to a basis of vectors for the vector space. And each basis element corresponds to a result of the measure. And not necessarily a possible result, we have to be careful about that word. We don't use that in technical sense. It corresponds to a potential result, shall I say, of a measurement. And any basis is a possible measurement. There's no orthogonality condition. Any basis is just as good as any other basis. And so what you do is you write your state vector in terms of the basis, and then the possible results are the ones which have non-zero components with respect to this basis. So that's how we identify the possible set. And that's it. There's no different coefficients corresponding to different elements of the field, non-zero elements of the field, all give you a possible result, and there's no distinction between them in the measurement theory. Now, note that a state vector and any scalar times that state vector gives you exactly the same set of possible results. So they're basically physically equivalent. This is analogous to the phase ambiguity in the state vector quantum mechanics. Pass that along. But notice there are no probabilities in our interpretation. Okay, good. Now, the simplest example is where our field is just Z2. And we have two-dimensional state space, and we call that a modal bit, or a mo bit, why not? And there are three pure states, there are just three states in it. There's the zero state, the one state, pick a computational basis. And then there's the superposition of 0 and 1. There's only one such superposition. And there are three possible measurement bases, and for old time's sake, we call them X, Y, and Z. The Z basis is the 0, 1 basis, but then the X basis is the 1 sigma basis, and the Y basis is the sigma 0 basis. They're all perfectly good bases. And there aren't very many states. There are 15 states for two mobits, of which 6 are entangled. Although if you have bigger systems, the number of entangled states becomes the great majority of states. But for mobits, states, 0 and 1 states, are present in the superposition, so the result 0 is possible. But if you make a y basis measurement, then only the sigma basis state, the plus y basis element, occurs in that superposition, and so the result corresponding to the 0 vector is not possible. The point being that, in general, we must consider the entire basis in order to determine whether a result is possible. We can't just look at it individual outcome by outcome. Let's take a look at an entangled state of two moments. The 0, 1 plus 1, 0 state, you can call it the singlet state. It has some properties analogous to the singlet state of two spins. If you make the same measurement on both sides of it, you always get opposite results. It's a very nice property of this state. But if you make different measurements, well, then it turns out that there are, of the 4 potential results, only 3 are possible, and 1 is impossible. So, for example, if you make the ZX combined measurement result, the result plus minus doesn't occur in the superposition. So one of the results is impossible. Okay, so this is sort of a way of describing the correlations between two entangled mopeds. So that raises an interesting question: how strange is this entanglement? In actual quantum mechanics, entanglement can be pretty strange. So, for example, could there be hidden variables? So could these correlations arise according to local modal hidden variables? There's a set of possible joint measurement outcomes, and we're just drawing from that set. So suppose the results of the measurement all exist in some sense. So we'll write that as the XYZ results for the first moped, and then on the other side we'll write the XYZ results for the second moped. And there are a bunch of 6 tuples. There are 64 potential 6 tuples. Which ones of these are possible? Well, the first thing to note is because corresponding measurements must disagree, we can throw out all but 8 of them. There are only 8 possible 6 tuples, or 8 potential 6 tuples that are consistent with a known behavior of two mopeds. But now let's look at non-parallel measurements. For example, if you measure the XZ combination, then as we said before, there's no possible, it should be ZX, but anyway, we get no plus-minus result. And so that means that those two possible sets of outcomes can't occur either. And if we consider all of the different possibilities, we find that there are several things that we have to throw away. And in fact, we have to throw away all of them. And what this means is that our original assumption can't explain the set of possible results we see from the two mopeds. And therefore, no local hidden variable theory can account for the correlations in this singlet-like state of two mopeds. There's a kind of Bell's theorem for modal quantum theory. You can have mixed states as well as pure states. For a mixed state, I just consider a mixture, a set of possible moped states. And two mixtures, two different such sets, are equivalent if they lead to the same possible measurement outcomes. And it turns out that we can identify these equivalence classes of mixtures with subspaces. And you can also have an analogy to an entangled, to a partial trace, and you can different things here. But this leads us to a no-cloning theorem. The no-cloning theorem holds. It's due to the linearity of the dynamics. The proof is almost exactly the same as that given by Wooters and Zurich almost 30 years ago. It turns out that if a cloning machine works for 2 states, it won't work for the superposition of those 2 states. Okay, so no cloning machine can work for all states in modal quantum theory. So, last slide. Modal quantum theory has a lot of characteristics. One set of characteristics are the things that it doesn't have. It doesn't have a lot of the aspects of actual quantum theory. There are no probabilities. You don't have a continuous set of states or operators play a much more restricted role. They describe the dynamics, but not really the states or the measurement results. And because you have neither effect operators nor density operators, you don't really have a kind of that close linkage between them that seems very special in actual quantum theory. Here's some things that modal quantum theory does have. It has classical versus quantum theories, just modal logic, propositional logic versus the modal quantum theory. You have superposition and interference effects. In Z2 modal quantum theory, all interference is destructive, because 1 plus 1 is 0. You have complementarity and different possible measurements you can make. You have linear dynamics in this discrete time. You have a perfectly sensible measurement theory. You have pure states and mixed states. You have entanglement. You have steering of ensembles, or steering of mixtures based on choice of measurement. You have a no local hidden variable theorem. You have a no cloning theorem. And you have lots more. There's a lot you can do with this. So here's my point. A lot of the structures that have been considered at this meeting depend on all, or at least most of, the things on the left-hand side. But here's a theory which is a lot like quantum mechanics. Has a lot of the flavor of quantum mechanics, has a lot of the quantum, there's a lot of really interesting things, which has none of these things. And it has all of these things. So, how can we extend our concepts to consider this kind of theory? And it should. So, that's my question.
Well, maybe a quick question while Renew should come down.
So if I'm trying to compare this to Rob's theory, quantum mechanics in general, I see you've got something actually extra, which is like explicit contextuality in a very strong sense, right? That your probability on
No probabilities.
No, I mean like the possibility. The possibility depends on the choice of measurements for one or two.
Yes. That's right.
Is that kind of, does that play a role, you think, in the fact of not finding any variable?
Does that play a role in not finding hidden variables? I don't know how to separate out those two aspects of the theory.
So this reminds me of a foil theory by Ernst Becker from 1960. But let me ask a question just to make sure it's right. Is it the case that for one mobit, there are 3 possible measurements, any pair of which can be done jointly?
No.
No.
No. They're complementary because a measurement is defined as a basis.
Okay.
If you have 2 measurements, then you have in fact all the vectors in the space for the mobit.
But there are 3 choices of bases.
There are 3 choices of bases, but they all overlap each other.
Right.
I have 3 vectors in the space. The 3 vectors in the space, any 2 of which form a basis.
Right. So I think of a basis as a measurement. You have 3 measurements, 3 pairs of 3 bases. But you can't do 2 measurements
I
at
can't
the
do 2
same time.
measurements.
It's just they overlap on one outcome.
They overlap on one outcome, but that's not that, because of this contextuality, I can't, from the outcome directly directly answer the question of whether that outcome is possible or not.
So there's no, this effect versus not this effect measurement.
Correct.
Okay, that makes it different from Specker's
Yes.
theory. Okay, thank you.
So I also have a question, but I'll leave it for lunch.
Okay.
So let's thank Renew. Renew Snapside. It's all over.
I wanted to say this is very preliminary and naive work, so thank you for putting me up on the short presentation. I was hoping that A to B, receive a proposition, B receives it in A's name, or a public broadcast of M by A, which is a simultaneous send and receive. On the quantum part, we can have preparation, so here A is preparing qubit I, such that if somebody measures in basis gamma, is going to see the classical result J. A projection, so he is projecting a qubit I using this base gamma and sees the classical result J, and then probably also some entanglement action. So these commands are like commands of measuring calculus of Kasheffield and some percussion. We need to add information, bring in some information concept to the setting. So how about I add these maps, fa of x, which I'm going to read out uncertainty, choices, possibilities of agent A about x. This can be a proposition, in which case fa of x is all the propositions A considers as true, when in reality x holds. X can be an action, in which case fa of x is all the actions A considered as happening, when in reality action X is happening. Here are some examples. The people who do some action, they have no uncertainty about the action, thus there are uncertainty maps identity. For example, if A does this preparation, fa of the preparation action is itself. However, A has a lot of uncertainty about actions done by other agents. For example, if A does this measurement, this projection, there are a lot of things that can be randomized. So what does A think? If B does an X projection and sees value 1, either X did a 0, either B did an X measurement and saw 0, either he did an X measurement and saw 1, did a Z and saw 1, or did a Z and saw 0, given that we restrict the measurement basis to X and Z. So this disjunction is the set of all possibilities that A has about B's actions. Now here is a very naive way to obtain an algebra from this data. I'm going to create a quantile of actions over the atom. The quantile is a complete lattice monoid. Then I'm going to generate a right module from my quantile using the propositions over the atoms that I introduced before. And then also very naively, I'm going to translate, for example, some laws of quantum theory from measurement calculus to this setting and quotient this over these laws. Here is like one obvious one. If there is a preparation such that somebody measures in X, this is a 1. Indeed, if he measures in X, he will see a 1. So this composition, so the dots are the actions of the quantile on the module, and this is the proposition. And I want this partial order to hold in the module. This guy is the classical result of the measurement. And then you also want to bring in some communication actions into this axiom. These are invariant under most of the communication actions. And we get something which I'm going to call a quantum system. So systems, the pair quantum module have been used widely, have been used in computer science as algebraic alternatives to prove correctness of programs, for example by Samsung. And these guys are called systems, the pair MQs. So why not when we quotient this, we call it a quantum system. W is for weird, the set of quantum axioms. And we bring in the uncertainties into the setting by endomorphisms of the module. And endomorphisms of the quantile, these have to satisfy some decomposition axioms with regard to the action of the quantile on the module and the monoid multiplication of the quantile. And obviously they preserve all the joints, they are scoop maps. And then when we add these things to the system, previously when there wasn't quantum stuff, I called it epistemic systems. So here is our quantum information systems. Automatically, we obtain some sort of a logic to write down properties we're interested in. For example, the action of the quantile on the module preserves all the joints. If you fix the quantile argument, action. So I'll replace it with a sequence, and then I'm going to distribute the FA to the sequence of actions of the Modal. I get this piece. And then I'm going to replace this FAs with their value of identity mostly everywhere except for when A is guessing about, this should be a P, sorry, the actions of P, then we get this big disjunct, and then these are disjunctions of the Modal, so they distribute over the composition. So I'll get 4 branches to verify, and then I'm going to bring in the axioms of the quantum and the complication axioms. So for example, the first one is impossible since A has prepared the qubit such that an X measurement will get the result 1. It's impossible that if P does an X measurement, we will see a result 0, so I'm going to send this to bottom, etc. And then I prove what I was after. However, there is so these kind of properties are not all the things that I want to be able to prove. For example, before we announce as broadcast is result X, so notice that here these last 2 branches become bottom because X is announcing his measurement basis. So if he measures Z, he is not going to announce Z and X. That's why these 2 branches get eliminated as a result of this broadcast. So if there is no broadcast, I cannot prove that A knows that the result of this measurement was 1. End of story. But this is not enough because I would like these 2 guys stay dangling, they stay around, so that's why I cannot prove this. But I would like to actually prove something A knows, and actually we all know that in 2 out of 3 of B's choices of possibilities, the value of B's measurement is actually 1. So I would like to prove that A believes with degree 2/3 that B is going to get a 1 after he measures. So you can also cook up more interesting versions of these degrees of belief if there was an intruder present. So that's one motivation why we need probabilities. Now, so this is the naivest way that came to my mind, that the probabilities are actually literally sitting in the setting. All you need to know is to count. Why? Because I've created both my module and the quantile over a set of atoms. So every element therein can be written down as a join of the atoms below, right? So I'm going to define a measure for every element of the module. In particular, I'm interested in the uncertainties. So the measure of A's uncertainty about X is n if and only if there are n atoms in FA of X. So this is as if I'm saying all the atoms that happen in A's uncertainty about X have a uniform probability of happening of 1 over this measure. Now, if you look in Wikipedia under channel information theory, you will see that they say the entropy of the system is in proportion with the set of possibilities of the system and the probability of each possibility. Now, they call this a maximal entropy if all these possibilities are uniform and equally the same. So here, if there are n choices, n uniform choices in A's uncertainty about X, is as if I'm saying that maximal entropy of A about X is minus log of n. So that's why the maximum entropy is independent. So to be able to derive the properties that I showed before, I'm going to add this new rule to my setting. So if X is true, A knows, A believes with degree k over n that y, if and only if k out of n of A's choices about X are below y, I probably want to say at least. And this is exactly what this thing here is encoding. Now actually I have to prove these things that before the announcement, A knows with degree 2 over 3 that 1. After the announcement, this degree increases to 1. I can also show that if there is an intruder present, and that we can stop A's qubit measure is prepare another one according to what we saw said it to be, then we get these numbers instead. So E is so we can put the classical version of the protocol and see why is it worse than the quantum version, why the quantum version is more interesting. Here is one possible scenario. Assume that here, the intruder, when he stops executing, actually copies it. So he copies it, sends one to Bob, and then measures the other one in the safe of his house. And you can show that his degree of knowledge is going to increase from 5/9 to 6/9. So we don't want the degree of knowledge of the intruder to increase, so that's why the classical version is bad. And then you see, as I showed, if there is an intruder present, there is no way Alice and Bob are going to share that secret, because the intruder will always have some good chance of knowing these things. So what do the quantum informaticians come up as a solution? They say, okay, we're going to do security amplification, run this protocol 1,000 times. Then Alice and Bob are going to pre-agree on a function that can XOR, apply to the results, because they can only guess the function, he has to guess more, thus his degree of information decreases. Then we can also model this here. For example, Alice and Bob run the protocol twice and take the XOR of the result. Then you can see that even if he is very, very lucky in his luckiest case, the degree of information is going to decrease. That's good. And here is another scenario. And again, you see that the degree of his information is going to go down to 6/27. Yeah, that's it.
Sorry, I got slowed down again.